Hey everyone, and welcome back to this class, Artificial Intelligence Reinforcement Learning in Python. Now let's get into some technical detail. Of course, you can never sense the entire world at once. Even humans don't do this. We have sensors which feed signals to our brain from the environment. These signals don't tell us everything about the room we're in, much less the world. So we necessarily have limited information about our environment, as do robots with limited numbers and types of sensors. The measurements we get from these sensors, sight, sound, and touch, make up a state. In this course, we'll only look at environments where there are a small, finite number of states. But of course, it's possible to consider environments with an infinite number of states too. Let's consider a simple example. Consider a tic-tac-toe board where we don't care about who wins, we just want to put X's and O's on the board. The board starts out as empty, and we continue to add X's or O's until the board is full. If you don't know how tic-tac-toe works, you can do a Google search and play the game yourself in the browser, directly in the search results. Remember that tic-tac-toe boards are 3x3 boards. What is the total number of states in this environment? I'll give you a minute to think about that, and then you can come back to the lecture. Since we're not considering a tic-tac-toe game where there is a winner after you get 3 X's or 3 O's in a row, this problem is very simple. Each location on the board has 3 possible states, empty, X, or O. There are 9 locations on the board, so the total number of states is 3 to the power 9. Let's recap the terms we've talked about so far. There are 3 of them, and possibly more that I snuck in. The 3 important ones are agent, which is the thing that senses the environment and the thing we're trying to code intelligence and learning into. There's the environment. This is the real world or simulated world that your agent lives in. Then there's the concept of state. These are different configurations of the environment that the agent can sense. There are a couple more things to define in reinforcement learning that are central to the subject. First, there is the concept of reward. This is what differentiates reinforcement learning algorithms from other kinds of machine learning algorithms. An agent will try to maximize not only its immediate reward, but future rewards as well. Often, reinforcement learning algorithms will find novel ways of accomplishing this. I'm not a Go player myself, but we've heard that the AlphaGo program learned unique and unpredictable strategies that led to its beating a world champion at Go. These are things that aren't intuitive to humans, but reinforcement learning algorithms can automatically figure them out. One potentially dangerous aspect of this is the idea of unintended consequences. We've all heard about the idea that an AI could potentially wipe out humanity if it decides that is the best thing for us. Imagine you program your AI to minimize the number of human deaths. And then it decides that since humanity is going to grow exponentially, and hence more people are going to die as well, then it would be better to destroy everyone now in order to minimize more dying in the future. So there is some danger of unintended and dangerous side effects for AIs that are interacting with the real world. To give you a more low-level example of how and why rewards should be programmed intelligently, think of a robot trying to solve a maze. A reasonable goal might be to simply solve the maze. If you solve the maze, you get a reward of 1, otherwise you get a reward of 0. With this reward structure, it's possible for a robot to just implement a random strategy and eventually solve the maze. Because we never told the robot that it should try to solve the maze efficiently, then making random movements until the maze is solved still gets you the reward. Now imagine that we give a reward of -1 for every step the AI takes in the maze. Now the AI has incentive to solve the maze using the least number of steps, and so it will tend to find a more efficient solution this way. We'll demonstrate this in code later in the course. Notice how a negative reward is like a penalty, which it is. Reward is just the term we always use. It tells you how good or bad you're doing. Note that the reward is always a real number. So now we've defined these terms: agent, environment, state, and reward, which is the thing we just talked about. The last important concept we need to talk about is actions. Actions are what the agent does in its environment. For example, if you're a 2D video game character, your actions might be up, down, left, right, and jump. This is an example of a finite set of actions. There are also examples of an infinite set of actions, but we won't discuss that in this course, unless the course is updated in the future to include them. The last three things we talked about are often thought about as a triple. You're in a state, you take an action, and you get a reward. We call these SAR, or state action reward triples. In reinforcement learning, timing is an important concept as well, since every time you play a game, you get a sequence of states, actions, and rewards. Within this framework, you start in a state S of t, you take an action A of t, but you receive a reward of R of t plus 1. So the reward you get always results from the state and action you took in the previous step. This action also results in you being in a new state, S of t plus 1. So another important triple is S of t, A of t, and S of t plus 1. Usually we just denote this as SAS prime. So that's reinforcement learning in a nutshell. You program the agent to try to be intelligent. The agent interacts with its environment by being in a state, taking an action based on that state, which then brings it to another state. The environment gives the agent a reward, either positive or negative, when it arrives in the next state, and the goal of the agent is to maximize its total rewards.